Okay, let's talk about section 6.1, Introduction to Exponential and Logarithmic Functions. Okay, so we're going to use what we did in chapter 5, in particular that composition stuff and inverse stuff, to talk about what lots of people are terrified of, logarithms. We're going to develop a little bit of what we're going to talk about here. But we first start with what an exponential function is. We've studied a bunch of different types of functions, haven't we? We had linear functions, rational functions, we had radical functions, we had polynomial functions, all these things, right? So an exponential function, it's just telling us where we're putting the variable, right? So this guy here, our variable, is up in the exponent position, and b is just some number. With b bigger than 0, b not 1. So a couple of things we might want to talk about here real fast, because this is going to be important for us when we start doing inverses. We might want to think about why we would not want to choose numbers that are, well, less than 0, or why we might not want to choose 1. So let's think about 1 first. If I had my function f is 1 to the x power, that's not very interesting, right? We know that 1 to the x is 1 for any x, right? Right? If I put in the exponent, if I square 1, hey, it's still 1. If I raise 1 to the negative 2 power, right, 1 to the negative 2, this would be 1 over 1 square, which is still just 1, right? So this is highly uninteresting because it's a constant function, so we're just not even going to think about it. We're not going to worry about it. Something else we might want to think about is having a number, maybe negative 2. If I have this number that's less than 0, if we think about what we usually do with functions, we usually make a table, pick our nice buddies, 0, 1, negative 1, maybe put another couple in there. And we can find function values, right? Negative 2 to the negative 2 power, that's going to be what? 1 over negative 2 to the 2, which is 1/4. I didn't leave myself enough space there. Negative 2 now to the negative 1 power. We would have 1 over negative 2. Okay, put a 0 in there. We're going to get negative 2 to the 0, which is just 1. Negative 2 to the 1. This is negative 2, rather. Oops. Negative 2. And then negative 2 squared, this is 4. So looking at our outputs here, we're going from positive to negative to positive. So if we would drew a picture of this, we would, be all over the place here, up and down, up and down. So here's why we don't think about these, because when we think about positive numbers, our signs aren't going to change like that. So goofy stuff isn't going to happen. So it's going to be smooth and continuous. It's going to be so beautiful. Okay, so we need to choose a number b, or for our base, that is both bigger than 0 and not 1. So this splits us up into two distinct intervals, right? If I'm thinking about a number line, I can't be 0 or anything less, so I have to be on the right side of 0, and I can't be 1. So this splits us up into two distinct intervals, right? This one and this one. So if our base is bigger than 1, it's in that interval 1 to infinity. So picking something easy, maybe let's say b equal 2. And over here, we can do the same thing at the same time here, right? Well, let's pick f of x equal something between 0 and 1. I think a natural choice based on that one would be 1/2, right? Okay, so let's just do what we usually do with functions. We're going to pick out function values, pick out x values out of our domain. We don't quite know what our domain is yet, but let me call this g just so that we're not talking about the same function. So x and then g of x. So pick out the same numbers. Okay, so thinking real quick about the domain. We're wanting numbers that I can put into an exponent position. We know from our previous coursework or the previous things we've done even this semester, we can put any number we want up in that exponent position, right? We can put negative things, we can put positive things, we can even put 0 in there. So any real number is going to be the domain here, and we can take a look at what happens. So if I put in x equal -2, my function value is going to be 2 to the -2 power, and we know that that just flips us into the denominator. So we've got 1 over, I was thinking 4 and I wrote 4. I should have been thinking 2 and writing 4 in the next step, right? 2 squared is 4. And then we've got 2 to the -1 equals 1 over 2. 2 to the 0. We know that anything to the 0 power is always 1. 2 to the 1, that's just 2. 2 to the 2, that's just 4. Okay, so we can draw a little graph here. So -2 goes with 1/4, that's like there. -1 goes with 1/2, a little higher. 0 goes with 1, 1 goes with 2, 2 goes with 4. Okay, so we know that if the domain is all the real numbers, I can put in numbers between what we've already got, right? And if we really wanted to, we could crank these values out with a calculator, but we're not going to do that. From our previous work with continuous domains, when the domain is continuous, that means that we can just connect the dots, right? So we can connect the dots. And we do. Okay, so now we have to think about what happens as x goes toward infinity here. What happens? Well, think about putting bigger numbers in here, right? So pick, 3, 4, 5 and see what happens. Or something really, really big, like if I put in 100, then I would have 2 to the 100 power, and that's super huge, right? So as we go to the right, as our x goes toward infinity, our function values are also going to go toward infinity, so they're going to shoot right up. As x goes toward the other direction now, well, where's that going to go? Pick out other numbers, right? Pick out smaller things, like if I put in -100, then I could say 2 to the -100. Well, that's going to be, I'm kind of in the way here, right? So if I would do 2 to the -100, that's 1 over 2 to the 100. So that's really, really close to 0, isn't it? So we can conclude from that we're going to go towards 0, and that's going to be what we've called in the past asymptotic behavior, right? Okay, so great, we did that one, and now we can have the one on the right-hand side, so we have a base that's between 0 and 1, 1/2. So we can do the same thing with this function g, right? So 1/2 here, 1/2 to the -2. Well, we know that when we have a negative exponent, it just flips over our fraction, and then that'd be a +2, excuse me. So it flips over the fraction, so we got 2, and then square it. So this is 4. Okay, -1, I'd have +1/2 to the -1 power. This is just 2 to the 1. 1/2 to the 0, that's just 1, because 0, anything to the 0 power is always 1. 1/2 to the 1 is just 1/2, and then 2 to the, excuse me, I keep writing my x value in there. So we got 1/2 to the 2, this is 1 over 4. So we can do the same thing with our little picture here that we did on the other side. -2, +2. So -2 goes with 4, -1 goes with 2, 0 goes with 1, and then we can probably notice that, right? That happened in this one too, didn't it? That is going to be a big deal. 1 goes with 1/2, and then we go to 1/4. And we can say something similar here, right? As x goes toward infinity, we probably, without too much mental work, we can see what happens, right? So on this one, as we go from left to right, as x goes toward infinity, our function value is going to go toward 0, right? And we can see that as x goes toward infinity, toward the negative direction, our function value is going to do the opposite of what the other one did, right? It's going to go toward infinity. So it looks like these things are reflections of each other. So we go way up. Okay, cool. So some things that we ought to notice about this. A few things we've already said here is our domain is all the real numbers, right? We can put any number I want in an exponent position, and that's fine. It's going to work out. The range of f, so the range of both of these, we can't get a negative number out of that deal, right? As long as our b is positive, these values are all going to be, well, positive. Raise a positive number to any exponent, it's always going to be positive. So the range is going to be all the positive numbers. This is true, right? F of 0 was 1. If I put a 0 in an exponent position, I always get 1. So that means that the point 0, 1 has to be on the graph of f. And we did have that asymptotic behavior, right? Y equals 0 was a horizontal asymptote. Okay, so these things. Yeah, right? We drew the graph. This is a consequence of having domain all the real numbers, that continuous and smooth business. The one-to-oneness, we can maybe explain this away in a couple of ways, because this one-to-oneness is going to be a big important deal for us. So think about what this graph, maybe this one on the left, looks like. We can think about what we've talked about before, right? If the function is ever increasing or decreasing or constant, it doesn't look like this function is ever constant or decreasing, right? This function here is always increasing. It's always going up. Always going up. So it's always increasing, which implies to us that it has to be one-to-one, because if it's always increasing, we're never going to repeat any function values. On the same note, if I'm always decreasing, if our function is always decreasing, going down, then as we move left to right, we're never going to repeat function values for that one either. So f is 1-to-1. So that should get some wheels turning, because in the last few sections we said stuff about one-to-one functions having inverses. If a function is one-to-one, it must have an inverse. So that's kind of going to be the big difficulty of what we're going to do. Let's find the inverse. Okay, so we just follow the steps that we had in the last section, right? We're going to replace f of x notation with y. We're going to switch x and y around, and then solve for y. Well, what do we do? Because we can't just subtract. We want to get the thing out of the exponent position, right? So we kind of turn our wheels a little bit, try a few things, and nothing really works. So what is going to work is we're going to invent something, and it's going to be called logarithm. So what we can say in words here, and I very much encourage you to think about this in words. Y is the exponent on B to get x. So it's the exponent we put on B to get x, right? B to the y power is x. So this in words is what logarithm is. So we use notation, and I hope it's coming up here. Yeah, there it is. So we use this notation right here to mean the exponent on B that gives us x. So it's the exponent that we put on the number B to get x. So we got, yeah, the notation here. So it's called a base B logarithm. And the expression here is read log base B of x. So for example, log base 2 of 8. This is the exponent on 2 that gives us 8. So, and we know what that is, right? We know that 2 to the third is 8, so that has to be 3, right? Okay. So more notation pieces here. The common logarithm. This happens so often with a base of 10 that we just don't write it. This is like saying 1 times x is equal to x, right? It's the same thing. We don't write the 1 because it's just there, right? And we know it's there without writing it. So when we don't write a base, the base is x. And then the natural logarithm, we haven't talked really all that much about this number e, but that is coming. So we will talk about the number e. But when the base is e, we're just going to write this natural log, that ln business. Whoa, that was kind of, there, that's back. That's back. Okay, good. So we can have properties of this function now, right? So something we should take from the last section is the properties of inverses in general. Remember this? So the domains and ranges flip-flop. Every statement that we're going to make about x is now a statement about y, and vice versa, right? So when we have properties of logarithm functions, well, the domain and the range are just going to switch. So the domain of a logarithm function is the range of the exponential function, and the range of f, a logarithm function, is the domain of an exponential function. So those guys switched around. Okay, well, the inverse of this, the exponential function, when I put in 0, gave us 1. So when we put in 1 to the logarithm function, it ought to give us 0, right? And maybe we can look at some a specific example of this. So if I have log base, I don't know, 2 of 0, or of x rather. What am I trying to do here? Log base 2 of x. So if this is my function, I can do f of 1. So this is log base 2 of 1. So this is the exponent that we raised 2 to get 1. Well, that's, 0. If I have a 1 in that position at all, ever, the only number I can use in an exponent to get to that 1 is going to be 0, right? Any number to the 0 power is always 1. So the point 1, 0 must be on the graph of our logarithm function. Remember, we had a horizontal asymptote for our exponential, so that's going to turn into a vertical asymptote, right? All the x's and y's switch, and that's that. What am I doing here? Okay, so it's 1 to 1, smooth and continuous. This is based on what we knew about. Sorry about that. Based on what we knew about inverses, we knew a couple of different things, right? If this is my exponential function, I can draw you what the logarithm function would have to look like, right? Because we know that functions and their inverses are reflections over the line y equal x, aren't they? So all of these points on that curve are going to be reflected over that line. So this is going to be our logarithm function. Let me get some more room here, and we can draw a very specific one. All right. Well, let's think about the same bases we used for the exponential ones, right? So if I want to draw, switch that to green. If I want to draw f equal log base 2 at x, we can do the same thing if we want to, right, with that little x and y chart. But we have to be more careful about what values that we use here in this x column. So we know that this is the exponent on 2 that gives us x. So this is the exponent on 2 that gives x. So any x value that we put in here, if we're going to have an easy, clean value to work with, it's going to have to be a power of 2. So maybe we can remember what we did for those other ordered pairs up on the first example we did with y equal 2 to the x, right? We just picked kind of anything we wanted, and we could just flip-flop those ordered pairs as well if we wanted to find numbers here. But let's just give some powers of 2 here. So the powers of 2 we want to think about are precisely the ones that we had for that last example. So maybe 1/4, 1/2, 1. 1 is a power of 2, isn't it? 2 is a power of 2, 4 is a power of 2, and we could say what the function value would be. So what's the exponent on 2 that's going to get us to 1/4? Well, it's -2, right? And then what's the exponent we put on 1/2 to get to 2? Well, -1. Exponent we put on 1 to get, or excuse me, the exponent that we put on 2 to get to 1, that's 0. The exponent that we put on 2 to get to 2 is 1, and then to get to 4 we have a square. So we can draw the picture. 1/4. So 1/4 goes with -2, so we're going to be like down here. 1/2 goes with -1, so that's about yay. 1, 0 is there. 2, 1 is there. 4, 2 is there. So that looks an awful lot like that, right? And we should notice, again, that, hey, we've got our reflection about the y-axis would give us our exponential function, just like we did up here. So here is y equal log base 2 of x. Here is y equal 2 to the x. So lo and behold, they are reflections of each other about that line. Okay, so we don't want to get too crazy about the graph and stuff at this point, but we should be thinking about it. So something that might be useful for us is graphing these things, because we're going to have to graph transformations. What we should do is do the easy thing. We notice that these guys have to be reflections of each other. So if I wanted to draw the graph of, say, I don't know, y equal log base 5 of x, and maybe I don't know what that looks like, we should think about the function y equals 5 to the x, because I can find ordered pairs on this function and just flip-flop x and y around, and then I'd have ordered pairs from that function. Okay, that's somehow easier for us. Okay, so yeah, this kind of sums up just exactly what logarithm is, right? Lots of textbooks just use this for their definition of logarithm, right? B to the a equals c, if and only if log base b of c is a. So a is the exponent that we put on b to get c. Yeah, great. Okay, let's use that one time real fast. So going back to the drawing graphs, let's sketch a graph of, let's have something that's a little complicated. So maybe y equal log base 2, and then let's have x plus 1 minus 3. So if we think about this with our transformations, and we probably should, the picture here is going to look just like that one, isn't it? But we're going to move it left 1 unit, and we're going to move it down 3 units. So let's pretend like we didn't do the exercise above, and we can talk about how to draw this graph if we're not sure what the standard log base 2 function looks like. Because we can just rewrite it using exponents. So rewrite with exponents. Okay, so first thing we want to do is isolate that logarithm stuff. So let's add 3 to both sides. So y plus 3 equals log base 2 x plus 1. Okay. So we can do this. And what would we have? Well, this object is the exponent that we put on 2 to get to x plus 1. So this thing is the exponent that I put on 2 if I want to get x plus 1. So 2 to the y plus 3 power has to be x plus 1, right? And this is exactly that definition, right? So 2 to this power has to be x plus 1. So that's what we've got. So these two equations are equivalent to the same thing. Okay, well, if I wanted to find the inverse, we're switching x and y around, right? So we would have 2 and then x plus 3, and then our y would be on that side now. So then solving this for y, we would have 2 to the x plus 3 minus 1. And now this is the inverse of this. So these are inverses. Well, what we can do now is we can find points on this graph, and we can just flip-flop the ordered pairs, and we can have points on the logarithm graph. So if we want to pick out numbers here for this, we'd probably want to stick around where this is going to be either -2, -1, 0, 1, or 2. So we can be kind of savvy with the way we pick our numbers here. So let's pick -5, and then that would give us 2 to the -5 plus 3, so that's -2 minus 1. So that's 1/4 minus 1, so -3/4. Okay, if I put in -4, we would have 2 to the -1 minus 1, so that's 1/2 minus 1, so that's -1/2. If I put in -3, we would have 2 to the 0 minus 1, so that's 1 minus 1 is 0. If we put in -2, that's going to give us 2 to the 1 minus 1, so that's 1. If I put in -1, that's going to give us 2 to the 2 minus 1, so that's 4 minus 1 is 3. And then we can draw our picture, right? So points on the inverse, we can just flip-flop the ordered pairs, and we're going to have points that are on the graph of our original function. So flip-flopping those ordered pairs, still need some more room here. So ordered pairs on our original function would be the opposite, or those guys flip-flopped. So we would have -3/4 goes with -5. We would have -1/2 goes with -4. We'd have 0 goes with -3. 1 goes with -2. 3 goes with -1. And then we can draw our graph. So -3/4 goes with -5. 1, 2, 3, 4, 5. So that's like there. 0 goes with -3. -1/2 goes with -4, so that's about yay. Okay. 1 goes with -2. 3 goes with -1. And so on. We can, connect the dots. How beautiful. Okay, cool. So there's one way to draw these graphs, and by thinking of the inverses. Because, I don't know, somehow the exponential functions are easier to deal with than logarithmic functions. Okay, good. So next comes some tricks that we can do. This thing here. Let's think about this in words here. That's an exponent, right? This is the exponent that we raise b to. To get b to the x, right? Well, what exponent are you going to put on b if you want to get b to the x power? Well, isn't that just x? And then this, that's the exponent on b to get x. Well, if I want to put some power on b to get x, well, what are you going to get? Are we going to get x? Right? Okay, so thinking about this in words, hopefully that makes sense, right? We're having the exponent on b that we want to get b to the x power. Well, x has to be that exponent. Similar thing with that other one. What we ought to also have in mind here is what we talked about in those previous sections, right? We know, I don't think we're going to use this right now. What we know is that if I compose a function with its inverse or an inverse with the original function, either way, we've got to get x, right? So what if we say f of x is b to the x, and then f inverse is the inverse of this thing, so this is log base b of x. Well, isn't that what we've got there? So with these, if I plug that in, I put f of f inverse, that would be b to the log base b x. Well, that has to be x. And if I do the other direction, I would have log base b of b to the x. Well, it's got to be x. Okay, so we should be able to reason our way through this with words, but this inverse stuff is pretty important. So these are both, well, x. Okay, so now we're going to use these a couple of times. The trick to using these is just to get our base, both of our bases to be the same, and then we can conclude what those have to be. So we can go ahead and do this. So log base 3 of 81. So we want to write 81 with a base of 3. It might help to do factor tree, I guess. This is 3 times 27. This is 3 times 9. And that's 3 times 3. So 81 is 3 to the 4th power. So we can write that as log base 3 of 3 to the 4th power, and we know that that's got to be 4. All right, cool. Didn't use up as much space as I thought we would. All right, so the next one, we got log base 2 of 1/8. So we want to write 1/8 with a base of 2. Well, log base 2, 1/8. We know that 8 is 2 cubed, and I would have to raise this to a negative power if I wanted to make it in the denominator, right? That's what negative in the exponent position does. So that means that this is going to be just -3. Okay, so now this one's a little bit more difficult. We're going to talk about things like this in a slightly different way in the next section. But essentially what we're doing is we want the exponent that I put on square root of 5 to get to 25. Right? That should be giving me an equal sign. So we want this thing. We know that 25 is 5 squared. So if I can rewrite this number with just a 5 there, we're going to be home free. So we know that 5 to the 1/2, that's what that is, right? And then we have 5 to the x over 2 is 5 to the 2. Okay. So now we have something that looks like some base to some power is the same as the same base to the same power. I don't want to get too terribly into this because we're going to talk about it in a future section, but it turns out that if we have a one-to-one function, remember what we had with one-to-one? One-to-one. We had kind of a mathy definition for this. We had if this is true, whoops, I want a y there. If f of x equals f of y, that means that x has to be y, right? When it's one-to-one. Well, we know that in particular, the exponential function is one-to-one. We talked about this, right? So this means that x has to be y here. So in our particular case, I've got the same base on both sides, so we can say, hey, x over 2 has to be 2. So that means that x has to be 4. We'll talk about these more later, but for now, we're kind of just halfway trying to reason our way through this. I mean, we could have started with square root of 5 and just multiplied it by itself until we get to 25, and we'll have to do it 4 times, right? Or we could say, square root of 5 squared is 5, and then 5 squared is 25. So I squared twice, which would be raising it to the 4th power. So, okay. Yeah, right now we're just trying to get these kind of by any means necessary, and we're going to do this sort of thing a lot more later. So, okay, good. So really, yeah, our strategy at this point is probably to just rewrite whatever number is in here in terms of just the base to some exponent. So we can do that with this one. That looks kind of ugly though. We know ln, that means natural log, so log base e. And then the object inside the parentheses here, we know that, just a little side note, I guess, this is the nth root of a to the m. This is a rational exponent, right? So we can say that this is e to the 2/3. And then we just conclude, hey, it's 2/3, right? Once we have the two bases here are the same, well, it's just got to be that exponent, right? So this is the exponent I raise e to. If I want to get e to the 2/3, well, it's 2/3. All right, 0.001. That's probably going to be better for us to think about this as a fraction. Also, we might want to put a base in there. So we've got log and then base 10, right? If we don't write it, it's base 10. And then let's write this thing as a fraction. So this is hundredths, no, that's tenths, hundredths, thousandths. So this is 1,000th. And now I want to rewrite 1 over 1,000 as a power of 10. So we know that 10 to the third is 1,000. So if I do 10 to the negative third, well, that's 1 over 1,000. Okay, and now I can just conclude that's -3. Okay, cool. So moving on, we have 2 raised to the power that I raised 2 to if I want to get 8. So if I raise 2 to the power that we raised 2 to get 8, shouldn't we get 8? And yeah, that's it. So we should get 8. Okay, this one here is just ever so slightly different, right? It kind of looks like the property we used right there, but the negative makes it so it's not the same. So we want to write that with a positive exponent. We know that negative exponents are just going to flip our number into the denominator. And then we have in the denominator that we can apply that property, right? 117 to the power you raise 117 to get 6. Well, it's going to give you a 6 in the denominator. So there you go. Is there another one? Oh, there's not. Okay. Well, cool. That was it for this section. So we started out and we talked about the graphs of these things, inverses of each other, right? Exponential functions and logarithmic functions are inverses of each other. What is going to be just dreadfully important for us is what's in this box right here. So this is what logarithm means, right? It's usually easier to think about exponential functions, and whenever we can, we kind of want to. So we can rephrase a logarithmic statement as an exponential statement, and that's going to be useful for us. Okay, great. Well, thanks for watching the video, and have a great rest of your day.